Welcome to Math with Professor V. In this video, we're going to learn how to find the real zeros of a polynomial function. So before we get started, we're going to have to go over 3 theorems that are going to help us do so. The first one states the following: the maximum number of zeros a polynomial function has is less than or equal to the degree of the polynomial. So what this is basically saying is, like if you have some polynomial, let's call it p of x, and it's 4x to the 6th minus 3x to the 5th plus 2x minus 7. The degree of this polynomial is 6, right? The highest power on the variable. And so I have 6 or fewer real zeros. And in this video, we're not going to be talking about or finding any imaginary zeros. That's coming up next. Right now, we're only focused on real solutions. So just keep in mind, for a polynomial, whatever the degree is, that's the maximum number of real zeros that we're going to be finding, okay? Now, how do we know when we find a zero? Well, we can use the factor theorem in a variety of ways. But basically, the factor theorem tells us a polynomial, f of x, has a factor x minus c if and only if f of c equals 0, meaning the remainder is 0. So what we're going to be doing for a lot of the video is using synthetic division to check whether or not a certain number is a zero of a polynomial. And what this boils down to basically is the following. Let me give you another little example that's not too crazy. Say you have q of x, and I'll give you something that you could just spot right off the bat, x squared minus 16, okay? We know that factors into x minus 4 and x plus 4. So if I were to synthetically divide q of x by x minus 4, for example, the remainder would be 0 because it factors, x minus 4 is a factor of q of x. So you could rewrite q of x divided by x minus 4 equals x plus 4, and there's no remainder. Also, if I just come along and simply plug in 4 for x, look what happens here. Q of 4 is 4 squared minus 16, which is 0. And that's what this is saying here. So when you have 0 remainder, that means x minus c basically is a factor, which also means if I substitute in c for x, I get 0. So a lot of different ways you can think about it, a lot of different ways you can check, and we're going to be utilizing all of this information. Now, the basis or the starting point for finding the real zeros is the rational zeros theorem. And it states the following: if the polynomial f of x, and then this is just listed, in generic form, it's a degree n polynomial, degree n, and then this is the constant term, a sub 0. If it has integer coefficients, and if p divided by q is a rational zero of f of x such that p and q have no common prime factor, then 1. The numerator p of the 0 is a factor of the constant term a naught, and 2. The denominator q of the 0 is a factor of the leading coefficient a sub n. This sounds a lot worse than it really is. So we're going to work through 2 little examples right now using the rational zeros theorem for you to see that it's not scary. Remember, a rational number is any number that you can write as a ratio of 2 integers. So it can be a fraction, absolutely, right? But what it can't be is some decimal that repeats, that has no repeating pattern that goes on forever. If you need a little breakdown of what a rational versus an irrational number is, I have a short little video, so I'll link it here and in the description. But let's just practice using the rational zeros theorem. And what it basically tells us is all of the potential rational zeros can be found by listing every single factor of the last term, the constant term, divided by all of the factors of the coefficient of the leading term. So the problem asks us to do the following: list the potential rational zeros of each polynomial function. Do not attempt to actually find the zeros. Okay, so I'm going to list all of the factors of the constant term 2. What are the factors of 2? Just 1 and 2. And I'm going to divide that by all of the factors of the coefficient of the leading term, which is 6. So what are all the factors of 6? Let's see. We've got 1, 2, 3, and 6. Yes? And then all of these could be positive or negative. So I'm going to add plus or minus in front of this list. And then I have to make every single possible pairing. So what do I mean by that? So we're going to have 1 divided by 1. That's just 1. 1 divided by 2, 1/2, 1/3, 1/6. So those are options. 1/2, 1/3, 1/6. And then repeat. So 2 divided by 1, that's 2. 2 divided by 2 is 1. I already have that on the list. Then we have 2 divided by 3, 2/3. And then 2 divided by 6 is 1/3, which I already have on the list. So these are all the possible rational zeros. How many are there? 1, 2, 3, 4, 5, 6. And then since I have positive and negative, then there's 12 possible rational zeros. Are all 12 of those going to work? Absolutely not. The degree of this polynomial is 4. It's only degree 4. So at most, 4 of them are going to work. And you might be saying, well, Professor V, that doesn't sound like a very helpful list. 12? 12 options when only 4 are going to work? But you know what? 12 is better than infinitely many, because I know, for example, that positive 3 is not going to be a 0 of this polynomial. Positive 3 is a rational number, and it's not on this list. Also, 7, 0. I can go on and on. So if I'm testing or guessing rational zeros, I'm going to stick to this list. Okay? Now, you could have an irrational zero. Irrational maybe like square root of 3 or square root of 7. And that's obviously irrational, so it wouldn't be in this list, and it still could be a 0 here. But this does help us narrow our focus quite a bit. It's very helpful. Okay, let's try one more. So your answer is basically just all of these possible zeros, okay? F of x equals negative 3x cubed minus x squared plus x plus 10. Don't pay attention to anybody in the middle. Just the first and the last. And you're looking at all of the possible combinations of the factors of the last term, 10. So 1, 2, 5, 10, divided by all the factors of 3. Don't worry about the negative because we're putting plus or minus outside. So 1 and 3. So this is going to be plus or minus, and then make every single possible pairing. So we'll have 1, 1/3, 2, 2/3, 5, 5/3, 10, 10/3. And this would be your final answer. Okay, now this is obviously way more than we're actually going to have. At most, we'll have 3 real zeros, and this is 1, 2, 3, 4, 5, 6, 7, 8 times 2, 16 possible. Now, there's other rules that you can apply to help narrow down this list, like Descartes' rule of signs or finding upper bounds and whatnot. I'm not going to get into all of that in this video, but if you want a little bit more in-depth lecture, I'll link it in the description should you want to kind of delve deeper. But with this, we have enough tools to find the real zeros of a polynomial function. All right, so first example says, use the rational zeros theorem, that's the theorem we just went over, to find all real zeros of each polynomial function, and then use the zeros to factor f over the real numbers. I'll show you how to do that at the end. It's pretty straightforward. So first things first, I want you to look at f and tell me what degree it is. That way we know max how many solutions we're going to be finding. It's degree 3, right? Okay, good. And then before you jump in and start listing plus or minus all of the factors of the constant term over the leading term, I want you to notice something. You can factor a 3 out from everybody, and that's going to help us a lot because 30 has so many factors. We would have the longest list from the rational zeros theorem. It would be frightening. So I'm going to rewrite f of x. It's 3 times x cubed plus 2x squared minus 15, or, oh, excuse me, minus 5x minus 10. Good? Okay, so now I'm just going to focus on this constant term and then the coefficient of x cubed, which is now 1. So plus or minus, all of the factors of 10 are 1, 2, 5, and 10, divided by all of the factors of just 1. So that's 1. So my list is just plus or minus 1, 2, 5, and 10. Okay, so what you're going to do is just guess from this list. Like I mentioned, we have other tools like Descartes' rule of signs and theorems on upper and lower bounds. So if you want to go through and watch the other video lecture to narrow down this list, feel free. But I'm just going to jump right in and just guess somebody from here. Use synthetic division to see if that is a 0 of this polynomial here. So I'm going to synthetically divide one of these numbers into this polynomial here. If I get remainder 0, then I know it's a 0 and that x minus that number is a factor. So just guess somebody who looks friendly. How about 1? 1's looking friendly. And then remember, when we do synthetic division, you just list the coefficients from each of the terms in descending order. So 1 for 1x cubed, 2 for 2x squared, negative 5, and then negative 10. And then leave yourself a blank row. The first entry on the left, you just bring it down. Don't do anything to it. And then here we multiply always on the diagonal. So 1 times 1 is 1, and I list that in the next column right there. And then you're going to add now vertically. So 2 plus 1, that's 3. And then same thing, you're going to multiply on the diagonal. 1 times 3, that's 3. Then add negative 2. Multiply negative 2, add negative 12. That's my remainder, that very last entry. Since it's not 0, that means x minus 1 is not a factor of f of x. And f of 1 does not equal 0. So x equals 1 is not a 0 of this particular polynomial. So that one didn't work. So guess somebody else from the list. 1 didn't work. Let's try 2. Actually, let's not depress ourselves. Let's try negative 2. Just because I've done this already, I don't want to drag this out. So 1, 2, negative 5, negative 10. Okay, so bring down the 1, multiply on the diagonal, add vertically, multiply on the diagonal, add vertically, 10, 0. Woohoo! It worked. This is remainder 0. Remainder 0. Which tells me f of negative 2, that's what I divided by, equals 0. And x minus negative 2 or x plus 2 is a factor of f of x. Now, at this point, we're done guessing. You don't have to keep going through the list to find the remaining zeros. Why do I say that? Well, what degree was our original polynomial? It was degree 3. Keep in mind this phrase, degree 2, home free. Degree 2, home free. Degree 2 means you can either factor or do the quadratic formula. You don't need to play this guessing game anymore. And once you successfully find a 0, down here, this is your quotient. It's always 1 degree lower than what you were dividing into originally. So this is degree 2. Now I'm home free. And this represents the coefficients of the polynomial that's degree 2. So it would be 1x squared plus 0x minus 5. If I just set this equal to 0, I can find the remaining 2 zeros of this polynomial function here. So x squared equals 5. I could just do the square root property. X equals plus or minus square root of 5. There they are. Those were not on the list up here because plus or minus square root of 5 are not rational numbers. Only rational zeros are in this list, see? But we do have all of them. So let me list it out. All of the zeros, I got all 3. It's negative 2, positive square root of 5, negative square root of 5. You could put plus or minus. I just really want to show that I've got 3 of them. You know what I mean? I'm like so proud. I got 3 zeros. And then we need to write f in factored form. So we kind of already started doing that. Don't forget, we pulled this 3 out front. And then I know this factors into x plus 2. And then it's other 2 zeros. So f of x is going to be 3 times. And then you always just do x minus each of the zeros. So we'll have 3 factors. It'll be x minus negative 2, which is x plus 2, x minus square root of 5, and then x plus square root of 5. And that's f completely factored. Good? Okay. So let's try some more examples just so you can build your practice and skills. Example B, f of x equals 2x to the 4th minus x cubed minus 5x squared plus 2x plus 2. So I can't factor out a common factor from the whole polynomial. Oh well. It's degree 4. So at most I'm going to find 4 real solutions. Now let's list all of the possible rational roots. So the factors of 2 are just 1 and 2. Over, again, the factors of 2 here, 1 and 2. So this leads me to all the following, plus or minus 1, 1/2, and then 2. So 6 options. That's not too bad. That's not too bad. So guess from the list, somebody, I'll guess 1, and I'm going to check if it's a 0 of the polynomial. So we're going to do synthetic division again, just list the coefficients. So we'll have 2, negative 1, negative 5, 2, 2. Leave your blank row. Bring down the entry all the way on the left. Don't do anything with it. Then you multiply here. So that's 2. Add vertically. That's 1. Keep it going. So 1, negative 4, negative 4, negative 2, negative 2, 0. Look at us go. So right away, I know that x equals 1 is a 0. So x minus 1 is a factor. Okay, how many more do I have to go? Well, there could be 3 more. I don't know. Here's the thing. You're going to guess somebody else from this list, but you're not going to divide it into the original. Because remember, what's the phrase I told you? Degree 2, home free. This is degree 4. Degree 4. This quotient is always 1 degree lower. So right now, this is degree 3. This is 2x cubed plus x squared minus 4x minus 2. You don't want to pick somebody from here and divide it into the original, because then you're going to get another quotient of degree 3 if it works. What I want to do is pick somebody from the list, divide it into this guy, because if it's a 0 of this reduced degree polynomial, of course it's going to be a 0 of the original. And then I can get this down to degree 2, and then I'm home free. Then I can factor or do the quadratic formula or whatnot. Okay, so once you get a 0 that works, keep it going. Don't divide into the original. Some books call this the depressed equation because it's been lowered by 1 degree compared to the original, but it's not sad, okay? So who should we pick from the list? I'm gonna go with negative 1/2. All right, and then see how you can just keep stacking it like this so nicely. All right, so bring down this entry, don't touch it. Then we multiply on the diagonal. So that's going to be negative 1. Then you add vertically. So that's 0. Multiply, add, multiply. Woohoo! We got another one. So that means x equals negative 1/2 is a 0. Yes? And then x plus 1/2 is a factor. Now we are home free because this is degree 2. This is 2x squared plus 0x minus 4. I'm going to set that equal to 0 and solve. You can just move the 4 over to the other side, because there's no middle term, no linear term, then I get x squared is 2. So x equals plus or minus the square root of 2. So those are my other two zeros. So here we go. We've got all 4. 1, negative 1/2, square root of 2, negative square root of 2. Good? Perfect. Okay, now we have to write f of x in factored form. And I want you to be careful when you do this. Look back here. You see how we had 2x squared minus 4? And then we divided by the 2 at this step. So when we write it in factored form, we have to bring that 2 back. If you want to remind yourself that it was there, because it's 2 times x squared minus 2, which is 2 times x plus rad 2 times x minus rad 2. So my point in highlighting all of this is that you need to add that 2 outside when writing it in factored form. And then you could put all your zeros. Then you have x plus rad 2, x minus rad 2, x minus 1, and x plus 1/2. Okay? The other way to remember that you need a 2 out front is because you see how this factor had a fraction with denominator 2. And if you look at the original equation, none of the coefficients were fractions. They were all integers. So then you go, if I were to multiply this all out, I'd have a bunch of 1/2s. So there needs to be a 2 that would get rid of that. Yes? Because there weren't any fractional coefficients here in the original. Okay, so that's that. That's just one little detail that I didn't want you to get tripped up by. How are we doing? All right, let's look at a couple more examples where the directions are just a wee bit different, but you're doing the same thing basically, okay? Solve each equation in the real number system. So here we have an equation. The left-hand side is a polynomial. It's set equal to 0. If I look at the degree, it's degree 5. So I have at most 5 solutions total, okay? So let's list all of the possible rational roots, and we're just going to start our little guessing party. So we'll have plus or minus all of the factors of 6. So what is that? 1, 2, 3, 6. Divided by all of the factors of 3. So 1 and 3. And this gives me plus or minus 1, 1/3, 2, 2/3, 3, 1, which I already have, 6, and then 2, which I already have. So here's all the options. Okay, let's pick somebody and just start plugging away. I'm going to guess 1. So we've got 3, -10, -6, 24, 11, -6. I need to find 3 until I'm home free. Because this is degree 5, we want to get down to degree 2. So bring this 3 down, multiply on the diagonal, add vertically. Let's see. -13, 11. Ooh, I'm getting excited. 11. Oh, dang it. 22, 22. No. Okay. So +1 did not work. Pick somebody else. Let's go with -1. So 3, -10, -6, 24, 11, -6. And I always tell my students, you know, if you're doing your homework after a couple guesses, if you can't get one, just graph this polynomial on Desmos or something, and then you can see where the zeros are, where it crosses the x-axis, and then just, guess one of those guys, because I don't want you sitting there just having bad attempt after bad attempt. It's depressing. Okay, bring the 3 down, multiply. That's -3, -13, +13, 7, -7, 17, -17. Is this going somewhere? I think so. -6, +6. Woohoo! Hallelujah. Okay, so that means x equals -1 is a 0. X plus 1 is a factor. And then I'm going to keep dividing into this quotient here, which is now degree 4. Remember, we started with degree 5, so it's 1 degree lower. So go back to the list. Let's see. Let's do 1/3. I'm going to do 1/3 because I don't want you to hate on the fractions. A lot of the time students don't like them, but it's like, what if they're the solution and you've just been avoiding them needlessly? 1/3 times 3, that's 1. Look at this, is not terrible. 1/3 times -12, -4. This is 3. 3 times 1/3, 1. 18, 6, 0. Bravo. I knew that was going to happen. I solved them all ahead of time. I have to confess. Okay, so then this tells me x equals 1/3 is a 0. And then x minus 1/3 is a factor. Okay. Now, this is down to degree 3. Let's double check. We started with degree 5. So this is degree 4. Degree 3, I just need one more. Let's guess 3. See how that works. 3 times 3, 9, -3, -9, -6, -18, 0. Yay! So then I know x equals 3 is a 0. And then x minus 3 is a factor. I don't think they asked me to factor in this one. So here's degree 2. Now we're home free. So we've got 3x squared minus 3x minus 6. Let me set that equal to 0. I can factor out a 3, and then I have x squared minus x minus 2 equals 0. That factors, right? Into x minus 2 times x plus 1. And then if I use the zero product property, then I have x minus 2 is 0, which means x equals 2 is the 0 of the equation. And then x plus 1 is 0, so x equals -1 is also a 0. So this time, it asked me to solve the equation. So I'm going to put all the answers in a solution set. And I want you to notice something. We got x equals -1 here initially, and then we got it again. So it's a 0 of multiplicity 2. It's in there twice. You don't have to actually list it twice in the solution set, but just know it's counting for 2 zeros. And then we also had 1/3, 3, and 2. So I know it looks like there's only 4 solutions, but this one is a double, multiplicity 2. That's my solution set. They didn't ask for us to factor the left-hand side, but we totally can if we want, because we have all the zeros, right? So if we wanted to write it in factored form, you'd have x plus 1 squared, because it's multiplicity 2. And then x minus 1/3, x minus 3, x minus 2 equals 0. And you do need a 3 out front because of that 1/3. And remember, we pulled out that 3 right there. Okay, they didn't ask for the factored form, but why not? Let's just show them we have a full skill set going on. And then I have one more example for you guys. Don't worry, it's a lower degree. So at most, we'll find 3 solutions. Let's list all the possible rational roots. So all of the factors of 20. Whew. 1, 2, 4, 5, 10, and 20. Over all the factors of 3. So 1 and 3. Okay, so this is going to be plus or minus 1, 1/3, 2, 2/3, 4, 4/3, holy smokes, 5, 5/3, 10, 10/3, 20, 20/3. I would never put something like this on an exam for my students because there's just too many options, you know? So you just got to guess somebody from the list. And I don't want you to suffer. I'm going to tell you, let's try 4/3. Okay. Like I said, if you're one of my students, I would just honestly, after 1 or 2 guesses, if you're not getting something, graph it in Desmos. 3, -1, 11, -20. Now, since this is degree 3 to start, I only need to find one from the list that works, because then the quotient will be degree 2 and we'll be in business. We'll be home free. Bring down the 3. 3 times 4/3 is 4. 3. This is 3 times 4/3, that's 4 again. This is 15. 15 times 4/3 is 20. Woohoo! We got it. So x equals 4/3 is a 0. And then here, this is degree 2 now. So we have 3x squared plus 3x plus 15 equals 0. Let's try to solve. I can take out a 3, and then I have x squared plus x plus 5 is 0. And this doesn't factor, now does it? So then we try the quadratic formula, because there's possibly 2 more zeros that we could find. So x equals opposite of b plus or minus square root b squared minus 4ac all over 2a. And this is going to be -1 plus or minus square root 1 minus 20, which is -19 over 2. As soon as I notice there's a negative underneath the radical, I know this isn't going to give me any real solutions. So we're done for this particular problem in this section, because we're only being asked to find real solutions. But in the very next lesson, I'm going to show you how to continue. So when you simplify square root of -19, it becomes I square root of 19, and then this is over 2. And here are actually the 2 other solutions, because remember, it's degree 3. So if we allow non-real solutions, complex or imaginary solutions, then you will always have the same number of solutions as the degree of the polynomial. And that's basically what the fundamental theorem of algebra states. So we're going to get into that next time. But here's the remaining 2. One for the positive, one for the negative. Since they're not real though, I'm not going to list them in the solution set. So the only solution we have is 4/3 all by its lonesome. This is the only real solution. Okay, so that concludes the lesson. If you need more help with solving equations or any of these topics, then head on over to the pre-calculus video lectures playlist, because I go more in depth. This is just kind of like a brief little overview in case you're solving equations again in your calculus class, or you just needed a little refresher. Give the video a thumbs up, subscribe if you haven't already, and then also follow me on Instagram and TikTok, Math with Professor V. I'll be back sooner than later. Don't worry, we'll solve some equations with complex solutions ASAP. Bye-bye.